Hello everyone, it's a pleasure to be here. My name is Bone2Gene from Bonn, and I would like to present to you our ongoing project on Bone2Gene, a deep learning-based diagnosis tool for diagnosis of rare skeletal disorders. I choose to start with a historical background. Skeletal disorders have been around throughout the recorded history, and we can find artifacts from different parts of the world, i.e. different ethnicities, depicting people with short stature. This is one. The classification of rare skeletal disorders have been already started as early as 17th century by the experts, but most of their diagnoses are reported later to be not correct. Perhaps the discovery that has revolutionized the field, which you all know took place here in Würzburg in the lab of Wilhelm Röntgen 5 minutes from here, was the discovery of X-ray, what he called Röntgen rays, that provided us with a different view of the whole world, including human body. X-ray have enabled scientists to differentiate different disorders based on their different characteristic features, and obviously caused an increase in the number of known different classes. The earliest serious efforts for classification of the skeletal disorders can be dated back to 1970s by various scientists, notably Jochen Spranger and Victor Martucci, that published nomenclatures of skeletal disorders. In addition, the rapid advances in sequencing technologies have helped identifying the genetic causes of these different many of the disorders, and also increase the number of different classes. To have a sense of that, in the article from Sepetifigo et al. 2001, they classify around 200 classes of skeletal disorders, and in the most recent Nosology and Classification publication in 2019, that number has increased to 461 classes, more than double in less than 1 decade. The pathogenic variant causing 437 of these 461 disorders are known. These are the genes I show here. You don't need to go through all of them, of course. The main point is that there are a lot. They are individually very rare, and in general, skeletal disorders are extremely heterogeneous. And all of these things makes the diagnosis of them a very challenging task. There are multiple inputs and ways and classes of approaches involved together for a final diagnosis, and you all know that one of the main ones is X-ray of human body, and also in measuring of the age of the bone to measure the maturity. This is where Bone2Gene is aiming to contribute. I don't go to the details of explaining what is the purpose. You have heard in the previous talks. We are training a deep neural convolutional neural network using hand X-ray images to build a tool that tells us the most probable, or the top 5 most probable disorders based on hand X-ray. The bulk of our data comes from Magdeburg and our colleagues in Magdeburg and Leipzig. These are 8 classes, 7 of them are disorders. We have also 79 healthy controls. The disorders are very wide: Turner, Noonan, Silver-Russell, hypochondroplasia, pseudohypoparathyroidism, and achondroplasia. As you can see, we also have some images from bone. This will increase, hopefully, and we don't aim to use them in the training process. We keep them in the final, for the final test. As you can see, the number of images is far from enough for training a neural network from scratch. You're seeing that in Face2Gene there are more than 200,000 or 20,000 images. So we need to use a technique called transfer learning. And for that, we use the public data from the Radiological Society of North America, RSNA, 14,000 images. These are the images for that the bone age for them have been measured by 7 different experts, and the average was given. So our neural network is of course much more complex than that, and that's also convolutional, not like this. But just for the sake of presentation, imagine that this is the neural network that you want to train. It's first initialized by random values, then after inputting many images and many training epochs, we reach to a trained model that is able to tell us the bone age. When it is a good model, then we transfer the knowledge of this model for the main task that we need, i.e. classification. We remove the last layer, we add different classes. Now we don't need to train the model from scratch. The knowledge has been transferred, but it's not optimal. So we continue a little bit more training, and we end up having a trained model, this time for classifying the disorders. So first we had to reach a good bone age model, which we did. This is our bone age, performance of our bone age model on the test set of the RSNA. It was published for a challenge, and the winner of the challenge also achieved a similar accuracy, a mean absolute difference of just 4.2 months. The average human rater uncertainty is slightly larger than that. Then we tested our bone age model on the unseen dysmorphic hands from the disorder data that we have collected, and it performs really well. Our pediatric colleagues have told us that this performance is good. And the mean absolute difference is 7.5 points only. This is then when we are convinced with the performance of the first model. Now we move to the transfer learning part, and then we trained a preliminary classifier for the classification of disorders. This is preliminary, and let's say that we see different accuracies for different classes. This is a confusion matrix on the diagonal of this confusion matrix. We see the accuracy of different classes, ranging from just 3% to 70%. On the non-diagonal ones, we can see how the model confuses different classes. For example, in the bottom row, there are 27% of Ulrich-Turner cases are correctly classified, but around 41% of them are incorrectly classified as a very wide syndrome. So confusion matrix can tell us something about the phenotypic similarity. For example, one point I should also add is that class predictions depend on two different factors at the same time. The number of images you have per class that model could see and be trained on, and the characteristic, distinctiveness of the characteristic features of different classes. Now going back to the confusions, there's a cluster here up there, achondroplasia, hypochondroplasia, and pseudohypoparathyroidism. There are different features that they have, but I just focus on the main ones, and all of them have brachydactyly, shortness of metacarpals and flanges. In the case of achondroplasia, oops, sorry, I have to that way. In the case of achondroplasia, the prominent feature is trident hand. And it's so distinct that despite we didn't have too many images, the model could pick that up and classify correctly. And in the case of hypochondroplasia, we have shortening of the fingers and metacarpals, but without trident finger. Again, the model could pick that up. And for pseudohypoparathyroidism, probably that's the reason that it's being confused, and some of them, in fact, a lot of them have been misclassified as hypochondroplasia, shortening, and we hope and we think that with increasing the number of images, the model will be able to differentiate these different classes. Another cluster that we see very well, and Ulrich-Turner, each of them have different characteristics. Again, here I show the ones that are similar between the two. In the case of Larry-Weil, there's a pyramidization of the carpal row. Although in the case of Ulrich-Turner it's different slightly, it's not exactly the same, but it's a similar thing. And the angles that trichoids from lunate and escaphoid make together, here this angle made by this green line, it's statistically lower in the case of Ulrich-Turner patients than normal. This is similar to that, the pyramidization. And also the short, so the metacarpals in the fourth and fifth fingers are shorter. These are probably the features that the model makes the model confused and makes it make wrong classification. I don't want to overinterpret the results of the model that we have now, but I just want to say that this part is preliminary. It shows that it's not giving unexpected results. Except from the fact that we know in general for deep learning and AI, that increasing the number of images and data per class increases the accuracy. We also know that if we have larger number of syndromes, that also increases the performance of the model, which is shown by a paper Sung already presented, that the increasing the number of syndromes increases the performance. That brings me to my summary slide. We have an excellent Bone2Gene model, which we are now working on technical aspects to deploy it as a tool that can be used for measuring the age of the bone. Based on that, and using transfer learning, we have built a preliminary classifier. We have 8 classes. The random probability is 1/8, 12.5%. The overall accuracy is now 40%. I understand if you're not impressed, but it shows that we are on the right track. And that's why we would like to invite the community to provide us with labeled hand X-ray data to make Bone2Gene a reliable tool for to assist diagnosis of rare skeletal disorders. And I stop here.
Yeah, I think this time there is time for a question. Do we have any from the audience? Yes, please.
You speak up. Speak up.
Ah, yeah, okay. You have shown some pictures from the patients, and have you also checked inside of the model whether these are also the features that your model is using for classification?
Not completely yet. Yes, we have tried with some saliency methods that we can see which part of the image the model has more attention to, but still we cannot say that it's exactly this or that part of the image. One point that also there was no time to mention is that in a lot of these disorders, this is the overall features of the hands that help the final diagnosis, the ratios of different bones, and so all the hand is taken into account. So if you use those kind of methods like saliency maps, the attention will be all over the hand. But this is definitely an important thing to do, and we are already thinking of methods to do that. But first, we need to increase the data to improve the performance of the model.
Cool.
Yeah, thanks, very interesting. So the hand, of course, has a lot of information already, but the second important part, of course, is the axial skeleton, so the spine. Is there any problem in using the spine for your image analysis, or why didn't you include it? Or is this the next step then?
It can be a next step, but as you know, the problem is usually data, and maybe Peter.
Yeah, transfer knowledge is also more difficult because you don't use it for age prediction, right? The spine.
Okay.
Yeah, we have a lot of data from hand that has been used for bone age measurement. It's a routine in many clinics, so we are confident that we can obtain hand X-rays, but spine would be very difficult in terms of data. But that would be very interesting.
Does it make sense to if I'm happy to contribute?
Yeah.
And X-rays, but does it make sense to also send you axial skeleton or like
Yes.
spine
Sure.
X-rays?
Yeah.
Okay.
Sure. Thank you.
Okay, in the interest of time, we actually have to move on. Thank you so much